So, hi everyone. The Bell 206L-4 Longranger that broke up over the Hudson River in New York on 10th April 2025 this year. This was yet another bad fatal accident and the 5 passengers who died here were just a happy family on a tour of the city. The lone pilot, with many hours of flying experience behind him, was also a victim. Now, for many weeks after this accident, I started to uh, work on it with whatever data I could get. I had to put off uploading this video until I closed my analysis in the AI 171 Dreamliner. So this video of mine, I found I could get my hands on a publicly available video footage of this accident from some tower around there, and I used that footage to actually extract all the image frames, enhance them, and I also managed to grab the acoustics quite well from that video footage. And then I managed to get to this stage, which identifying the rotor orders and the structural breakup events, the structural breakup, especially the tail boom. So these things came from the processing of the acoustic data and the images that I extracted out of there. And they strongly point to one single possibility, the most plausible thing, and that is a kind of jammed transmission, especially jamming of the tail rotor. Possibly this jamming was just momentary, but it was sufficient to really end up causing a total structural failure of the tail boom and ending up looking like this wreckage that was recovered by the NTSB in a day after that accident. And speaking of the NTSB, here is the report that came out a few days after the accident. And I think they've done a quite a good job in really highlighting a lot of facts about the flight and the maneuvers, the last minute of flight, and so on. The only thing I just want to point out here is they use the actual clock time at the Eastern Standard Time at the time of the accident. But I use a very different time reference here, and I don't use it actual clock time. And of course, it hardly matters here that different starting time reference. Anyway, so the big questions that I'm trying to address here is the why, the what, and the how, the whole work that I've done, I'm going to present here. So this video is really about trying to give some insight into the critical moments before the breakup. And in that insight, I mean, is something kind of, which a structural engineer would talk about with kind of results from signal processing, image processing, and such things available. And then, I've used only the publicly available video footage of the accident because there's no other official data from anyone. And I extracted everything from there, the image as well as the acoustic content, as I just mentioned. And my analyses are pretty standard. They don't use anything exotic or anything. Very everyday kind of analysis that one would do in the world of signal processing and image processing. I used something called scalograms, again a very standard approach to capturing, identifying, detecting phenomena which occur at very different time scales, like a very short duration event occurring on a long time scale. It's best captured through wavelet decomposition or a scaleogram. Now the NTSB itself, I think they had released footage of their recovery itself quite well, and that footage I used to really grab a few screenshots, and the link to that footage of the recovery video is on top here, the YouTube video. So in this screenshot, what you see here is kind of the part of the wreckage, the helicopter. You can see the bit of the tail boom here and the fuselage all broken up, of course. There's a section here that has failed in the tail boom, which is of course the where everything really has started. The entire helicopter's complete failure. And there are actually two modes of failure here that have happened: a tear failure and a delamitation failure. That these occur respectively in a tension zone and a compressive zone. And of course, the delamination refers to the mode of failure in a composite skin, which of course the tube, there's a tube wall is constructed out of the composite materials, I guess, here, carbon composite or whatever, with a mix of a hybrid composite possibly. The letters MH you see on this helicopter here, that's on the face. I call this the left face, and that face is actually the face that's on the edge that's coming, mating that face is really the one in tension, and the one on the other side which is facing the ground, opposite the MH face, is in the one in compression. Alright, so here's a second screenshot that's taken to show the this pale creamy region you see here is where the engine and main rotor are mounted. Again, to emphasize the tension phase that I'm talking about, it's where this person's official's palm is being placed on the glove. His palm is on the surface that's in tension, or at least dominantly in tension. All right, now here is the footage I'm talking about, which came from the tower some distance away. I call it bit recorded, and there's a YouTube link to it, and it's probably around 63 seconds or something like that, or maybe a little longer. But I trimmed it to something like 11 seconds window that really was sufficient for my needs to cover the pre-breakup stage of the flight up to the splash of some of these parts that came up after the breakup. So let's look at bit recorded now, and yeah, if you look closely, you can see the helicopter approaching from the left side. It is now behind the tower. This tower, it comes out of it. And break up. All the loud chugs that you hear are post the breakup. So see the piece splashing there, and I think other piece also splashes down a bit later. Yes. So the link to bit recorded is anyway here. You can get to that link and see it if you want to see it once again or something like that. Anyway, I'll move on with the analysis I have done here. So what I've done is I take the 11 seconds window of bit recorded. I call that still as bit recorded, though it's cropped to just 11 seconds, just for simplicity. And I go through, as I said, two analyses here. One is a yaw analysis and one is an acoustic analysis. Now, why yaw analysis? If you look, again, if you look at a video, for example, you'll see that the helicopter underwent a terrific yaw to the right. And that's what made me suspect that something there, and that had something to do with the breakup of the structure here. The acoustic analysis, of course, like the AI-171 that I studied earlier and in my previous videos, they gave me a lot of answers. In fact, the acoustic analysis were able to bring out what I think are the bangs that people heard. Some people were interviewed after this crash in the neighborhood of the river, and they heard, they said, yes, we heard a few bangs there before it broke up. So I think I've kind of zeroed in on those, what might be most likely the bangs. And I was also surprised that I could capture the rotor orders, though the tower, microphone and camera were probably nearly a kilometer away from the helicopter, and I think you could still hear a hum out there. Probably that was good enough to resolve the rotor orders too. But anyway, the final thing is, all these things lead me to kind of concluding that there was a tail boom breakup happened only from this rapid yaw. That's a very sharp, quick yaw. You'll see how quick it was in a while. Let's get to the yaw analysis for this purpose. So what I do is I take bit recorded, and I have done a bit of pre-processing here. So I extract frames, the images at various 0.1 seconds interval. Then of course I had to enhance them, because you can see bit recorded is pretty hazy, and I needed to bring them to sufficient clarity to really kind of confirm that the direction of yaw and things of that kind. So once I enhance it, I get a kind of high contrast grayscale frames, and then I take these grayscale frames and I crop them to a kind of small bounding box that contains the helicopter. So you can see one such little box here, a white box, white rectangle with, you can see the helicopter within it. That very dark part is the darkest part is the fuselage, and the little tail-like thing is that light glitter gray is the tail boom. The other parts of the helicopter, of course, are not that clearly visible here, because they're probably going too fast, or the rotors, for example, will be too fast are probably not very clear in the image taken that far away. Now I could have gone ahead with these bounding boxes and so on for the rest of the analysis, yaw analysis, but I chose to really convert this grayscale to jet color maps, which you see here on another small box here, because I found it a little easier to explain and understand and interpret. So let's look at a typical bounding box in the jet scale mode, something like this. So every such box comes at a certain frame instant. So this is at 0 second. 0 seconds is the very first frame that I extracted. And you see that the jet color map is really on a decibel scale, not on a normal amplitude scale. It's not a linear scale, it's a decibel scale, which is kind of logarithmic. So it kind of gives very strong exponential weighting to the more intense regions, and exponentially lower weighting to the less intense regions. So that's why you see dominantly, it's a kind of little kind of exponential filter, if you want to call it. You see dominantly, you see the deep red here and the light red here. Well, I'm going to come to that, what they are, and I guess you might already guess the deep red is fuselage, of course, and light red is the tail boom. Now what I do is, for any pixel like this sitting in the deep red region, I define I jet as this intensity of that at that pixel on this scale, the decibel scale, the dB scale. Now, in order to really isolate this fuselage and tail boom combination, the group, and why I want to do that is because obviously, if you want to recognize yaw in this helicopter, you do so by looking at the extent of tail boom that you see there from your point of where you're looking at it. So relative to this particular frame that you're now looking at, if there was a frame that where you hardly saw anything in the tail boom, so you're almost like looking along the tail boom, and yaw is almost 90 degrees from this position. So that's what I'm trying to do here as well. So I define a set called P10. P10 is the set of all pixels that fall in this minus 10 to 0 decibel range. That's the most intense reddish part zone of it. So that's because I kind of, as you can see from this color map, you would agree with me more or less that that's very reliable, kind of it reliably represents the fuselage and tail boom group there to high signal to noise ratio. All right, so now let's look at a GIF of this helicopter flight here. That GIF is going to play now, and just before I start, you just look at a little rectangle out here on the top, red rectangle box. The helicopter is in that box. It's always good to remain in that box throughout playing the GIF. And also look at the time on the bottom left corner, the 0.00 seconds that you see here, the time T. Okay, now let me play this, and you can look at the comparison of the time and the corresponding helicopter's position there. This is, by the way, this is one of the enhanced, this GIF has come from all the enhancement of frames. So it's much sharper, as you can see from the bit record that you saw a while ago. Okay, here it goes. So if you look at this, for example, at the start there is hardly any yaw, but somewhere around 1 second, I think you see a kind of nearly complete yaw. The helicopter is completely yawing to the right by 1 second. So that kind of, I used that kind of a fact now the next to really kind of determine the limits of the 0 degree yaw and the 90 degree yaw from this on the time scale. Now what exactly I've done is something like this. So at 0 seconds of that GIF, or the way I bit recorded, which I have used, you can see the helicopter looks like this. You hardly see any yaw in it. You could zoom it if you want to, but I think it's quite obvious from this jet map as well as from the enhanced thing that you don't see any yaw there. So I define theta as 0 degrees at 0 seconds. Now the other extreme, when you come to the 1 second stage, you see the yaw is almost complete. You're looking almost along the tail boom, so you hardly see even either of them, the jet map or the frame there. So this is 90 degrees at 1 second. All right. So now what I do is I have to get a relation with these two. I map the 1 second time to 90 degrees and the 0 second time to 0 degrees. So I just do a linear mapping of this time to angle. And how I do it is like this. I first determine the CG of P10 region, which is like finding the centroid of an area of varying density here. And then using this coordinate system here, the XYZ coordinate system, I call xp as the distance of any pixel p from that centroid. And then I compute a simple metric. This is something like a moment of inertia about this y-axis in the lying at CG. So that just comes from, the summation is, for all pixels that lie in P10. It's not from 1 to P10, but it implies that it's for all pixels that lie in P10. And then I kind of, this is always going to be positive. The xp squared makes it positive. And intensity is always there. And well, now what I do with this is obviously, because if you look at this particular frame, because this looks like a 0 degree frame. In fact, it is. So you would expect the IYY to be quite large for this particular frame. And correspondingly, when this comes to the 90 degree position, as you saw in that 2 frames I used a while ago, you would not expect much of the IYY. You would expect it to be quite small, much smaller than this. So that gives obviously relation kind of sets a relation here between the I and the theta. So I use the fraction of the thing, full I range. I mean that really get the mapping from 0 to 90. All that that's not as simple as it. It's just linear relation between them, between the I by 0 and I by at 1. All right. So now let's look at the results that I get from this. So this is what you get. The black points you see here, the data points, they are computed values of the I by the theta I at various time instants. Now, of course, I have to curve fit this because the helicopter isn't really going to jump from one theta to the next. It's actually moving continuously in time. So I had to do a curve fit. But because this is not such a simple classical smooth yaw, it's got something unusual about it. I had to go for a kind of 5-segment optimally placed knots cubic fit, so that the optimal knots in fact are what you see as its dashed lines segment boundaries, and this has got a very good correlation. You can see it's 99.6%. But the point to notice not this how pretty it looks here as fit, but rather this thing. The theta yaw is really jumping almost by 90 degrees, 83.6 degrees in just 0.4 seconds. That's as just I guess I don't know how fast it is compared to the time, much less than time it takes to blink an eye. Imagine a helicopter that's doing a nearly 90 degrees in that time. I'm sure that itself might have really done a hell of a lot of damage to everyone on board there, if not the structure. But of course, that what we know from the analysis is not what happened inside, but at least the structure is the one that obviously took the blow. And why it took blow and how it took it, we're going to see in a while. And I didn't go beyond 2 seconds because the helicopter's breakup itself happened at 2.2. So whatever I wanted to capture has happened in this 0.4 to 0.8 seconds. Okay, now let's look at the stress character under when it's in a normal flight without any yaw happening. It's a peaceful flight. So what you're looking at is a kind of very simplified representation of the fuselage and body, the tail boom here. That little piece you see at the very end of the tail boom is the axis of the tail rotor. So what I want to just bring out here is the kind of equilibrium of things when it's in normal flight without yaw. In that situation, you would find that the main rotor's torque, which I call as T main, would exactly be balanced by the torque coming from the tail rotor in order to keep that from yawing. And the tail rotor's torque is going to be F tail times DAC, the distance to the shear center. The shear center, by the way, is a imaginary location in this case of the shear flow that's happening in the fuselage due to this torque. So any book on aircraft structures would tell you more about the shear center, how to compute it for various cross sections and so on, but I'm not going to spend my time on that here. Anyway, the corresponding stresses that you see developed in the tail boom here, for a kind of this is more like a beam if you look at it from top. It's a beam that's really like a cantilever beam. For example, it's like anchored here and you have a load at the tip. So that will kind of cause a tension on the upper side here. So you see that tensile stress there. So that's a skin tensile stress. The bars here represent the magnitudes. And I have kind of made a bars go up from small level near the fuselage to high level near the tail is. Well, it's just a reasonable kind of picture that I would expect, because I can't simulate or numerically model anything yet because I don't have the data to do so. But you can see that the tail boom is tapering. So as your tail boom tapers, you get a drop in the moment of inertia associated with bending here. And concomitant with that drop, you would expect that the sigma has to go up to make up for the lack of moment of inertia. So I just roughly proved this kind of variation from the fuselage to tail boom. And again, on the counterpart on this side of the thing, the compressive thing would look like this correspondingly. Alright, so I call this sigma x6 normal. A normal means a peaceful flight without any yaw. Now let's look at the situation when there's a jam has happened in the tail rotor. So that means the tail rotor is not really able to deliver a torque. It's just seized momentarily from rotating. Now, if that happens, T main is still active, but there's no T tail. because F tail has been kind of is just momentarily stopped. So that means what? So the helicopter is now going to yaw, but yaw under is not a static situation but a dynamic one. So what's really taking place here is a kind of flexible body undergoing also a rigid body rotation, which is yaw. And why it's flexible is obviously because the tail boom is not a rigid body anyway. So you see it deformed like this. And indeed, the deformation is much like a cantilever deforming under tip load. But where is the tip load here? Well, it's a good question to ask. There's no tip load because F tail is 0. But in this case, it is not the tip load, but rather the inertial load that's sitting on the tail boom, coming from the tail boom. And that inertial load comes from all the mass of the tail boom here with of course, the mass of the tail rotor, which is very much there, that did not go away. Mass cannot be destroyed, it's still very much there, even if it's not doing anything. And that, associated with the acceleration, the angular acceleration, causes this kind of transverse load to act on the tail boom, which causes this deformation in turn. Alright, so now look at the stresses in this situation. You would see that it's quite different from the one that was there when it was kind of normal. So there's a peak somewhere between the fuselage and tip of the tail boom, somewhere there. And that place is the sigma x, the xx, the stress component in the normal to the xx phase. That's going to be very high, much higher than what you see in the normal situation. And the counterpart again, in the compressor side will also be something like this. You would see again a very large sigma xx the compressor side too. So obviously, what does it mean? Things are well outside, past their safe levels. So once they are past the safe levels, you do expect things to start failing. So there are certainly, well, it's not necessary that both failures, tensile and compressor, have to happen at the same time. They don't have to, and I can't even say which one happened first either, because that again depends on a lot of things, the margins that are there related to their respective modes. Anyway, the point is not to sit and wonder more and more and deeper into it, but at least try to qualitatively look at it like what I'm doing now. Right? In fact, so once this happens and you would expect something to fail here, and how it failed, look at this. So what does this tell you? If you look at the person's hand palm here, his palm is on the tensile side actually. And you see a kind of neat tear here that's across a group of rivets there. That's something like tearing off your check leaf from a checkbook. So you have perforations there which are precisely meant for this purpose. It's meant to tear exactly along the line of perforation, very neatly. And that's exactly what seems to have happened here. So this tensile failure here, you do see it happen. By the way, this, if my memory is right, I must acknowledge at this point a few of the other experts on YouTube who did talk about this long back. I think probably Captain Steve. I'm very sorry if I haven't acknowledged anybody else. It's not intentional because I'm not able to go through every one of the videos that have come on this to pick up every point, but at least I'm sure this is not the first time that has been said. Some people have rightly already observed that there was tension here on this side. And of course I concur with them. Yeah, that's a tear failure I was just talking about. And it's not necessary for the tear failure to happen all over the zone in tension. It's good enough if it happens over part of it. Because again, there's a circumferential distribution of this tensile stress. So if the failure margin is such that it's crossed a certain part of it, only a part of it, that part would fail. But once that fails, everything gets into nonlinear kind of evolution of failures. And let's look at the compressor side. So you can see this is another view of another screenshot, and just zoom that part here, which is which I want to highlight. Well, so what you see here is a kind of on the other side of it, not exactly very precisely on the other side, but somewhat kind of the other side of it. I mean, the other side means the other side to the tensile one. You do see failure of a very different kind. You don't see the kind of tear there, but kind of it looks more like a delamination in that zone. It's a bit hard to say exactly how much it's exactly opposite to the tensile side, but okay, it's kind of roughly agrees with what you would expect from a dual tension compression kind of character in the stress distribution. Alright, but I also feel when I look at that's the tear, and this kind of transmission shaft that's sitting there, To me, it looks like there was a shear stress failure on this. If I look at very closely, that kind of failed surface of that. Now, that's a serious thing, because if the transmission shaft was the first to fail due to this jamming, I would expect that that was the first failure to occur in the entire system, well before the structural failures too. So if that had happened, in fact, because of the jamming, yes, so that would have meant obviously a no tail rotor torque, and of course the rest of the story, just what I just mentioned a while ago. All right, now let's try to complement this with the acoustic analysis. Again, as I said, these things, I'm fortunate to have run into that video footage too, because it's not bad, I could still do a lot with that footage, notes from a public domain footage out there. So this is the acoustic amplitude that you hear from the microphone as a function of time. So the splash occurs somewhere around little past 9 seconds. If you can correlate it with the time in the bit recorded, if you look at the bit recorded. But what is really one should notice is this little burst that happened somewhere around early enough, I guess 0.4, 0.6 seconds, somewhere out there. So what I did was I just took the first 4 seconds of this, decided to take a very close look at that 4 seconds window. And I see this first, this is the 4 seconds window I'm talking about. Again, I do see that burst out there, and I thought that's really where all the answers to most of the questions are, and I put that part of the data through a scaleogram analysis, a wavelet decomposition. And this is what I first see when I get the very low acoustic amplitudes, very, very low acoustic energy levels. This is at minus 140 decibel scale, not a normal scale for anyone, far below what a human can hear. And the interesting thing is you see a sort of bright, shiny streaks here from 0 onwards up to some 0.5 seconds. Well, let's see what they are. The first streak that you see is the 1x. It's around 6 hertz. 6 hertz is around 360 kind of RPM. It's roughly around 6 hertz, say 6.2, whatever. It's 360 to 375 RPM is the known rotational RPM of a Bell helicopter. Well, it seems to be doing well all the way up to 0.45 seconds. And the next streak that you see a little above is a 2x1, which that would be the blade passing frequency. It's a twin blade rotor. So 2x thing. Well, I do see a third streak, a fourth streak, but I can't. I just have no clue what they are coming from, because I tried talking to Bell helicopters in India, but they would not give me any data on this thing for reasons best known to them. Nor could I get anything searching Vanon Aviation's website, the people who make the rotor blades. And of course, Rolls-Royce, I knew would not have much on its website on any engineering information on this, except a few numbers for customers' needs and so on. Anyway, so what we see here is the things are ending around 0.45 seconds, which is kind of agreeing well with that sharp yaw that we saw between 0.4 seconds and 0.8 seconds. So it looks like the rotors really, something happened there. So we don't know what exactly happened, but how exactly it happened. But anyway, they seem to agree. The stoppage of this rotors thing and the commencement of the sharp yaw. So if you go to the other extreme, the high frequency regime and also the high amplitude, this is what I see. So you see kind of two banks out here, two sharp bursts kind of thing. They are somewhere in the 1500 to 3000 kind of hertz range. This is pretty likely to have been a structural breakup kind of bang, because there's nothing in the helicopter that's going to be of these frequencies. None of the things run at its frequency anyway. No matter whichever order you look at, it's not going to be anywhere in this neighborhood of this 1500 to 2000 or 3000 hertz. They're all in a few hundreds of hertz, so at the most. So these things are certainly structural failures that have caused these bangs, and I guess these are the ones that people heard around them. And I've just said that this is the tensile zone, that's the compression zone. I might be wrong here because I don't know which happened first, but I just looked at the sharpness or the intensity. The tensile zone looks to me a bit sharper than the compressive zone, so I'm just guessing. But it doesn't matter here, because I think it's good enough if we could get this far from a publicly available video footage, and at least zero in on the moment that the structural failures really happen. So it's not that terribly important to know which happened first, the structure tensile one or the compressive one. Who cares anyway? It's the whole thing. What we have to, obviously need to look at is how to stop such things from happening again. All right, so I think I could summarize it in stage, and the first point is, of course, obviously, just reiterating it again, the high rate of yaw, an 83.6 degrees kind of thing, just 0.4 seconds. I think this itself would have been damaging to people inside, would have injured most people over probably even the pilot too, I don't know. And of course, the kilograms, we could see the rotor orders out there and the kind of precise moments, the structural failures that kind of bangs before the breakup. Now, well, if this very rapid speed of rate of yaw, in terms of structural mechanics language, it's kind of a high flexural load on the tail boom, and that's been induced by inertia, as I just mentioned a while ago. So that again, that severe load is slow. It would have been so severe to really cross all the margins or safe levels of the stresses there, and of course the breakup. This is the kind of explanation I have for the failure that hit us, the initiation of all the failures there. All right, I think so. It's the tail rotor transmission that certainly got jammed, not the main rotor. And why? Because there has been a very similar event in 1997 in Canada, where in this case, in this Canadian accident, the main rotor transmission was the one to have jammed. But fortunately, in this case, the pilot survived with his passengers. Great on their part, lucky that they all managed it. And after obviously they were able to really narrate some of the things that they saw there or heard there. So in fact, the pilot did warn his passengers to prepare for an emergency landing. But look at the point that here the pilot and passengers heard a loud bang before the helicopter yaw took place. So it is all in the neighborhood of this thing. Well, I'm not sure if the passengers heard the bang first and the yaw next, or whether they happened almost at the same time. Because if you look at the sequence of things here, they happened in just 0.4 seconds. So I'm sure people wouldn't be so precise in being able to say whether the yaw happened first or the bang happened first. Anyway, they all seem to be happening such quickly, one after another. So the point is, this helicopter yaw was sharply to the left, whereas in our case of this Bell Hudson crash, it is sharply yawing to the right. So yawing to the left would happen if the main rotor transmission were jammed, in which case the tail rotor thrust is trying to take it to the left. But yawing to the right would happen if the tail rotor transmission is jammed and the main rotor torque would take it to the right. Okay, so these things also, if you look at the video, the GIF, the video bit recorded, you would see that it is yawing to the right again in this particular case. All right. So 2 points I just want to bring out to close this. See, vibration has been highlighted off and on as a concern in the Bell class of helicopters. There have been some advisories from the NTSB, from Van Horn Aviation and others. Well, I don't know, but how much of re-engineering and how much of study was done on this to really, how exhaustively it was studied to really make sure it would not get into the way of causing a transmission jam here. I wouldn't be surprised if a transmission jam happened from vibration here, because whirling is one of the things that is concerned, especially when you have a rotation speed that's really coming in proximity to some kind of a structural frequency out there. That might have caused a transmission, possibly, I don't know, I can't say, I'm just guessing. But anyway, the real answer would come not from these kind of guesswork, but kind of minimalist black box system, which is what most people have been always saying, all the people who have been putting up videos on YouTube. See, a lot of speculation could just be put to rest with one such black box system, just at least a handful of parameters, some 7 to 8 parameters of the engine, the blades, the body accelerations, and also I guess about a 25 parameter kind of black box record would go a long way in kind of for satisfaction, but it's a very important thing in really preventing future crashes and accidents. It kind of helps design analysts to really get close to the root cause and the pinpoint the real cause of the whole failure. So that there's no, otherwise it's a lot of speculation all the time, and it's frustrating to people really who want to understand and make a better world, prevent accidents of this kind. Anyway, let me still, though it's more than many months now since the accident happened, I still pray for the victims' families, and I pray that God gives them strength. The loved ones who lost their families in this very tragic way. Family holidaying, just a 15-minute holiday tour of the city shouldn't have really been had this kind of fate, facing them. So let's hope that the future designs are really going to be much better than this, and someone out there, the manufacturers and designers across Rolls-Royce, the Van On Aviation, or over to Blade Manufacturing, and the helicopters companies too. I hope they all put their sit together and really work out some kind of a system that's like this black box system, or it would be the first step at least to really go a long way in preventing such crashes. Thank you.